Hi everyone, my name is Svoboda and I work at Apple on the Clang compiler. Today I'm excited to be talking about how we are improving the performance and reliability of modular builds by making modules an explicit part of the build system. Here are the topics that I want to cover today. Before I dive into the meat of this talk, let's take a look at why we think modules are great. The main reason is that textual inclusion is extremely fragile. It's way too easy for developers to accidentally leak preprocessor state from one file to another, which may silently change the semantics. Another pitfall of textual inclusion is that libraries unconditionally export all symbols, even those of its dependencies. When consuming a library, developers have no way of knowing which symbols are exported intentionally and which by accident due to the copy-paste nature of textual inclusion. Clang modules solve both of those issues. Modules isolate individual libraries into self-contained units of code, making them more robust. Clang compiles each module with a fresh preprocessor instance, completely eliminating leakage of preprocessor state. With Clang modules, library authors have a way to describe which symbols are to be exported, and the compiler is able to enforce this, making library APIs much cleaner and safer to use. Clang modules also help with compile times. Builds using textual inclusion are slow due to the quadratic complexity and the number of translation units and header files. Single header is pre-processed, tokenized, parsed, and analyzed as many times as it's included. Saying this is inefficient would be an understatement. With Clang modules, each module is compiled only once when it's first imported and gets stored on disk in a module cache. This binary representation can be loaded and efficiently reused by multiple translation units, which can significantly speed up build times. We are currently using what we call implicit modules. In this setup, modules are completely hidden from the build system, and the compiler builds them on the fly in the background. From the build system perspective, there is no difference between modular builds and builds using textual inclusion. All the build system needs to do is spawn a single compiler instance for each translation unit and profit. That's it. This makes it fairly easy to integrate modules into the traditional build model that we've been using since the dawn of time. And of course, we still get the isolation and performance benefits I just talked about. But over the time, we have discovered some problems of the implicit system. First of all, the compiler has become quite complex. Clang basically acts as a second build system that uses file locking for coordination, manages consistency of the on-disk module cache by rebuilding modules when inputs change, and takes care of evicting modules from the cache to free up disk space. This complexity makes it all too easy for bugs to creep in, and they are often difficult to troubleshoot. Moreover, compilation scheduling is subpar, since the build system doesn't know about compiles of modules. What often happens is that build system spawns multiple Clang invocations, assuming work will be done in parallel, but if they all need the same module, compiling it becomes responsibility of one invocation, while the rest sit idle. Implicit modules have also proven to be unreliable in certain situations. We'll look at those in a moment. And that's why we have decided to create a new system for compiling modular software. One where the build system has full awareness of Clang modules. The basic idea is that the build system has explicit knowledge of the structure of modular dependencies. This makes it possible to use its built-in scheduler to effectively pre-compile modules in the first step, and when that's done, compile the translation units themselves in the second step. The problem is, how do we make the build system aware of modular dependencies? We didn't want our users to manually duplicate the dependency information in the build description, since it's already present in their source code as includes or imports. So we have decided to scan the includes and imports in the source code and learn the structure of modular dependencies that way. To be able to do that efficiently, we have created the fast dependency scanner, which Alex Lorenz and Michael Spencer presented at EuroLLVM 3 years ago. With that, the build system then creates dynamic tasks for modular dependencies that each spawns Clang to precompile the module. When all dependencies have been built, the build system spawns the compiler for the translation unit itself. With this system in place, it's possible to take any project that works with implicit modules and compile it more efficiently using explicit modules instead. So what has the integration of modules into the build system brought us? Because the build system knows structure of the whole build, we get better scheduling. If multiple Clang invocations need the same module, it can be pre-compiled in parallel with other modules instead of blocking all invocations. As a bonus, it actually becomes possible to distribute the build across multiple machines. The build plan now contains fine-grained compilation tasks that each has a known set of input files. The compiler now becomes simpler since it doesn't have to implement its own build system, eliminating a lot of implementation bugs. And for us compiler engineers, it becomes much easier to debug build issues. We can see all compiles of modules in the build log as individual Clang invocations that we can copy-paste into our terminals and investigate without worrying about the state of the module cache. But how does the scanner communicate the dependencies with the build system? Well, we have created a libclang API, and here is an example usage. Let's try to compile a translation unit that imports some modules. All we need to know are the compiler arguments set up for implicit modules and the current working directory. First, the build system creates a scanning service, which holds some configuration and global state. Then, it creates one or more workers, each of which can scan one translation unit at a time. Finally, the build system calls the getFileDependencies function with one of the workers, the command line arguments, and the directory. Whenever the scanner discovers a modular dependency, it invokes the given callback. The build system using this API might choose to start compiling discovered modules right away, but we'll just collect them into this modules dependency set variable and make the callback a merge operation. This way, any newly discovered modular dependencies will be merged into this set. When the getFileDependencies function returns, the set will be describing the full graph of modular dependencies and directly or transitively imported by the given translation unit. The function also gives back the dependency information for the translation unit itself, which includes the set of direct modular dependencies and the command line, among other things. Finally, the build system can schedule the compile of discovered modules and the translation unit itself. Let's take a really quick look at how a naive implementation of that might look like. So for the translation unit, let's just compile the direct modular dependencies. And when that's done, compile the translation unit using the build arguments provided by the scanner. To compile a modular dependency, we can do the same. Let's just find its information in the dependency graph, recursively compile all its direct dependencies, and compile the module itself. This is a really naive implementation that omits error handling, doesn't dispose resources, and isn't particularly efficient. But I believe this should give you some idea how the whole thing works. We are fairly happy with this API, so we are working on upstreaming it and would like to get some feedback from the community. Now, let's switch gears for a bit and talk about the reliability aspect, as I promised earlier. Build of a project typically involves multiple translation units, and some of them are going to end up importing the same module. The problem is that each translation unit may be set up with a different set of compiler flags. Those can change the semantics of the program or behavior of the compiler. In other words, the translation unit is compiled in different contexts. For each translation unit, we need to make sure the modules it imports are compatible, that they obey those flags. The compiler can't build a module that's universal and that satisfies all possible flag combinations. This forces the compiler to build multiple versions of the same module. Compatibility between modules is dictated by the context hash, which is just a hash of the compiler flags. On the right-hand side of the slide, you can see an example of a project where two translation units use the same version of a module because they share the same context hash X, and a third translation unit that uses a different version of the same module, since it has a different context hash Y due to the different define flag. In the implicit module system, context hash includes only some compiler flags, actually only a very small subset of them. That increases performance. The compiler simply doesn't build as many modules. The problem is that translation units may end up using modules that are not compatible. Let's take a look at the example on the right-hand side again. Let's say module B contains declarations of some platform-specific intrinsic functions that are included from whichever header can be found in the search paths. Now, we have two translation units that specify an ARM-specific include directory. When compiling module B for those translation units, the ARM-specific directory will be used, and the module will contain AST with ARM intrinsics. When it comes to the third translation unit, though, it is configured with Intel-specific include directory. We'd expect a new version of module B to be compiled in order to pick up the expected Intel-specific header file. But context hash doesn't include the search paths at all. This means the context hash of the third translation unit is same as the first two. This tells the compiler that it's fine to import module B with ARM-specific intrinsics into the third translation unit. This is, of course, incorrect given the source code of module B. So we have seen how an imprecise context hash can lead to an import of incorrect AST. This is not a hypothetical scenario. We are actually seeing this happen in real projects. In the implicit system, Clang resolves some context hash collisions by recompiling the module again in place. We can't do that in the explicit system since the compiler isn't in control anymore. We'd like the system to be robust and to prevent these situations in the first place. That's why we'd really like to include all relevant compiler flags in the context hash. That guarantees correctness of modules sharing, which is great. Unfortunately, that explodes the number of modules we need to compile. When investigating what's the reason behind differences in compiler flags, we identified the search paths as the major cause. This makes sense when you think about it. Take the Clang project, for example. It encompasses a lot of command line tools, and the entry point of each lives in a separate CPP file in a distinct directory, which becomes a search path from the compiler's point of view. This means that if you build the Clang driver and decide to build Clang format later, you need to recompile all modules again. That's despite the fact that they will most likely not be affected by a search path that only contains a single CPP file. The cool thing about the scanner is that it can verify which search paths are actually being used. Unused search paths can be stripped out, essentially making the context hash more universal. And by doing this, the scanner is effectively merging parts of the dependency graph and reducing the number of modules we need to build. This is something the implicit system could never do. It needs the context hash before building the module, and it can identify used search paths only after compiling the module. In the end, the new system is correct. We no longer get invalid AST contents by importing modules that are not compatible. And it is almost as minimal as the implicit system. We only compile extra modules when we know that's necessary. Now let's talk about what's still ahead of us. We've got a new system that's more efficient and reliable than the old one, and that's cool. However, its greatest strength is the greatest weakness too. It requires tight build system integration. But there are lots of build systems out there, and we can't realistically make Clang modules explicit in all of them. Moreover, we have other tools that need to build modules, for example, the debugger or indexer, to name a few. Those tools don't always have a build system at hand, and embedding a build system into each of those tools is probably not the way to go. So one idea we have been playing with is a system that has the trivial build system API of implicit modules, but actually builds modules in more centralized and orchestrated way. We have something like this in mind. The build system, say make, is configured with some translation units, as usual. The build system invokes the compiler for each translation unit, and each compiler instance reports itself to some long-running Clang daemon. The daemon accepts requests from individual invocations, and for each of them, it scans dependencies of the translation unit and precompiles the modules. Then the daemon notifies the original compiler instance how to use those modules. And finally, the original Clang instance carries on with compilation of the translation unit. Compared to proper build system integration, this setup has some clear drawbacks. It has less context than the build system, since it learns about the translation units on the fly during compilation. Compare that with the build system with integration that can learn the whole dependency graph before actually compiling anything. And the daemon still needs to embed what's essentially a second build system with its own scheduling, handling of incremental builds, and so on. But we believe it gives us some nice wins. It's still given much more context than the compiler alone in the implicit system. It can actually schedule compiles of modules and provide stronger guarantees for their compatibility. The daemon could manage caches more effectively. For example, it could hold on to cached file system contents for the duration of a single build run, and reuse that between scans and module compiles. Next, the compiler becomes simpler. We can remove defensive checks for file system changes, context collisions, and so on, making our lives easier and shipping fewer bugs. And of course, this would be available in all toolchains using Clang, regardless of the build system. To sum up, let's see what we have accomplished. We have created fast scanner that figures out the graph of modular dependencies. We have a working build system integration built on the new libclang API, and we have some early adoption successes. Next, we want to explore the idea of Clang daemon for implicitly precompiling modules for tools that don't have a supported build system behind their back. Last but not least, we have some performance work left to do. The fast dependency scanner is not as fast as it could be, and there are leftovers from implicit modules in the compiler. Most notably, lots of defensive checks for file changes, which can be eliminated when a proper build system handles that for us. And with that, I'm happy to take questions.
Thank you very much, Jan. Questions, please. There is one in front.
Hello. Thank you for very interesting talk. I work on Clang tools. Is it possible to integrate this system and use it for Clang tools? Especially, I say about Clang tidy, Clang D, and so on. They have some specific compilation options. It can be tricky.
And the question is?
Can it be integrated and used for Clang tools?
I believe so, yeah. You could probably use the simple implicit modules API that we already have in place, maybe with some extra flag that says spawn the daemon in the background, or use it as a library call in the C++ API in tree.
Do you have any experience of using this build system for Clang tools? Or not yet? Or?
Not yet. We have a prototype, but nothing set in stone.
Okay, thank you.
Hey, thanks for the talk. Can you say a little bit about how this Clang daemon would work with distributed compiles? Like with DistCC or similar?
The question is if I could talk about the distributed compiles. Yeah, so the problem with implicit modules is that the compiler discovers work on the fly. So basically the build system has no way of knowing how to efficiently distribute files among the different machines. It doesn't know which files the compiler will require to compile the modules. And so with this system, the dependencies or the files that we need to compile a module, we already know after the quick dependency scan that can be done locally. So the build system can then decide which files to ship to the remote machine to compile the module remotely. And this is just not possible with implicit modules.
Thanks for the talk. So I have a question. So you mentioned performance quite a few times. Do you have some like ballpark numbers, like what you actually get with the explicit schedule, like if with actually knowing the explicit module dependencies and like better scheduling it? Like I guess like it's getting like you're doing like some testing, I guess, on the LLVM code base itself or something like that.
Yeah. So we don't have any definite numbers yet, and there's still a lot of work to do. I think we would be happy with maybe 10% gain of modules compile times on real projects. But if you have some pathological case like translation that includes a lot of modules that don't have any dependencies, you could basically go from linear complexity of the build in the number of modules you need to build to just like constant complexity, because you can compile everything in the same step in parallel instead of compiling one module at a time.
Wait, is that 10% compared to non-modules or to implicit modules?
To implicit modules.
All right, thanks.
Any more questions? I think we have a few minutes. Otherwise, thank you very much, Jan.
Thanks.